Hey everyone. Welcome back to Linear Algebra. This will be lecture 3 of the course. And in this section, we're going to discuss, we're going to introduce matrices, and then we're going to discuss some of the kind of fundamental operations of matrices. So let's go ahead and jump into that. So this will be section 1.3 and fundamental operations with matrices. Okay, and so for many people, you will probably have heard of the word matrix, obviously, but you may or may not have ever actually interacted with them, and so this may be an introduction to you. So let's go ahead and start with a definition. Okay, an n by m, well, I want to do it the other way, m by n matrix is a rectangular array of real numbers. Okay, a rectangular array of real numbers, and it's going to be arranged in m rows and n columns. Okay. All right, so that's more or less the idea. There are a couple of things about it. So the numbers of in the matrix, maybe better said that the elements in the matrix, numbers/elements in the matrix, are frequently called entries. And so, and I guess finally the m by n piece denotes the dimensions. Okay, so an m by n matrix is a rectangular array of real numbers arranged in m rows and n columns. The numbers or elements of the matrix are called entries, and the m by n denotes the dimensions. So that's kind of obvious from the preceding sentence. Let's take a look at an example or two here. All right, so 1, 2, 3, 4, 5, 6 as a matrix. This is a 2 by 3 matrix. All right, what about this? 1, 0, 0, 4, 3, 1. Is a 3 by 2 matrix. Right? 3 rows, 2 columns, 3 by 2. 2 rows, 3 columns, 2 by 3. Okay, what about this one? 1, 2, 3. This is a 3 by 1. Sorry. 1, 2, 3 is a 3 by 1. 3 rows, 1 column. And 1, 2, 3 is a 1 by 3. Right, 1 row, 3 columns. Okay, so these are just a few examples. Now it's a little bit up to you how you want to identify or how you want to denote matrices when you're actually writing them out like this. It's very common for just big almost like oversized parentheses to denote the boundaries of a matrix, or you may see brackets like this. It's completely up to you how you want to do it. I think I tend to gravitate towards this approach simply because it's faster, but it doesn't matter, right? Either one, it tells the same story. So okay, let's talk through just a few conventions. Just conventions regarding matrices. When we denote a matrix as using some kind of a name or a variable, we'll typically use a capitalized bold letter. To denote a matrix. So, for example, like A, B, or C. Right? The matrix A, the matrix B, the matrix C. It's not uncommon also to use sort of like an all capitalized letter with like a subscript. So C1, C2, etc. This is also something you'll see. What you rarely see are things like this, right? Lowercase letters. These are more typically used to denote, like a variable for a real number or something like that, right? It's not common for a matrix to be denoted that way. Okay, so that's not typically what we do. Okay. Very good. We already kind of discussed this, but just to emphasize, the size of the matrix is denoted as m by n, right, in the general case. So this means m rows by n columns. Right, so the thing to point out here is that the first entry in the m by n denotes the number of rows. It's always rows by columns. So that's just kind of a convention, and it just makes interpretation like easier and more with less ambiguity and things like that. And so the first entry is the number of rows. The second entry is the number of columns, and that's always right. You'll never find any other. Very rarely would you ever find any exception to that. Okay, and something else to think about. So is if you have an m by n matrix, you can think of it in terms of vectors. So an m by n matrix can be thought of as, so first you could think of it as a collection of m row vectors. Right? So each row of the matrix you can think of as being a vector. Right? And so if you have m row vectors, then each of them will have n entries. Right? That's one way to think about it. There's plenty of applications that use matrices in this way. Another way to think about it is as a collection of n column vectors. Right? And then in this case, each with m entries. Okay, so that's very very common as well, right? Lots and lots of applications for both of those. Okay. Now, frequently when we're trying to prove things about matrices, we will have to resort to discussing the entries of the matrix. And so in those instances, we will, so we'll often write Aij to denote the ij entry, well, to denote the entry of the matrix in the ith row and the jth column. Okay, so entry Aij will denote the ith row and jth column. Okay, so for example, let's say we have the matrix A, which is equal to, A11, A12, A21, A22. Right. So this is a 2 by 2 matrix. Right, and so I can easily see that this is this entry here, for example, is in row 1, column 1, A11. This entry over here is in row 1, column 2, so it's at A12. Okay, so this is the idea of this Aij. Now we'll frequently use just the generic Aij to denote the matrix itself, and you can comment, you may see this. right, to just refer to the matrix itself. In this sense, we're referring to a generic entry in the matrix. And when we have to reason about the entries of the matrix, we may use this notation. Okay. All right. Very good. Let's do one more example just to make sure this is really clear. So if I have matrix A equals 1, 3, 4, 2, 0, 7, then A11 would be the element in the first row, first column, so it's going to be equal to 1. What about A23? Well, that's going to be the element in the second row, third column. So second row, third column, that's going to be equal to 7, right? A12 would be equal to the first row, second column, so that would be equal to 3, etc., right? So just make sure that this notation is clear so you can follow what we mean when we say entry Aij being specific values, okay, not just the arbitrary values. Okay, all right, very good. Let's see. So when we talk about matrices, it's frequently useful to discuss the set of all m by n matrices. So the set of all m by n matrices with real number entries anyways can be denoted by mn, like this. There's different ways that I've seen people denote these things. So this is one way, m sub mn. I've also seen m and then people writing m by n like this. I think I've also seen m by n as well. I've seen all three of these. So there's just different ways to write it. Now what you're talking about is a set of matrices here. So for example, the set of matrices M12 would be equal to all of the matrices that are one row and two columns. So things like this. Right, something like that. Right? So it'd be just a set of all such matrices of this form. Right, M22. Right here we're talking about 2 by 2 matrices. Right, so that's a set of all 2 by 2 matrices. And so on. So it's just sometimes this notation will kind of come up, and it's just a way to denote like this infinite set of matrices of particular dimension. Okay. All right. Very good. The diagonal entries of a matrix will be of special importance. They're denoted in the natural way, but let's just point it out. They are denoted by, so A11, A22, A33, and so on. Right, and so you can see that in the case of like a 2 by 2, you have A11, A12, A21, A22. So the diagonal matrices are on the diagonal, and we refer to this as the main diagonal. Right, there are other diagonals in a matrix. In this one, there's definitely this other direction, diagonal, but this is what we mean when we say the main diagonal. You know, and in a matrix with more than 2 rows and 2 columns, there would be off main diagonals as well. So you might have a diagonal down here, for example, or up here. But when we talk about the diagonal of a matrix, we don't typically refer to those. We typically refer to this one, the main diagonal. Okay, very good. So just kind of fleshing out some ideas here. What does it mean for 2 matrices to be equal? So 2 matrices A and B are equal if and only if Aij is equal to Bij for all 1 less than or equal to I less than or equal to M, and for all 1 less than or equal to J less than or equal to N. So these, we say 2 M by N matrices, I should say. M by N. Okay, so basically the corresponding entries have to be the same. Okay, so A equals 1, 2, 3, 4, and B equals 1, 3, 2, 4. A is not equal to B, right? Because 1 is equal to 1, 4 is equal to 4, but 2 is not equal to 3, 3 is not equal to 2, right? So in particular, you could say A 1, 2 is not equal to B 1, 2. And you could also say A2, 1 is not equal to B2, 1. Right, so there are, that's a kind of a simple, explanation of what we mean by equality. Okay. All right. Okay. Let's talk through a few sort of special types of matrices that'll come up a ton in this course. So the first one that we can talk about is, so these are special types of matrices. The first one is just the square matrix. Right, and a square matrix is just what the name implies. It's a matrix with the same number of rows and columns. Okay. Now these will come up a ton, right? So there's a lot of things that are really interesting about matrices in general, but very many things that are specifically interesting about square matrices. So something like this is a square matrix. You know, another example would be something like that. All right, so this is 2 by 2, this is 4 by 4. Okay, square matrix. Another special type of matrix that'll come up in this course a lot is the diagonal matrix. Right, now this isn't a matrix that has a diagonal shape, it's a square matrix with all non-zero entries appearing only on the diagonal. Okay, so an example there would just be like this: 6, 0, 0, 0, 3, 0, 2, 0, 0, 0, 1. Right, so here's the main diagonal. Right, and you'll notice that off the main diagonal, everything is 0, 0, 0, 0, 0, 0, 0. Here's another example. Okay, this is another example of a diagonal matrix. Now in this case, all of the off-diagonal entries are 0, but you also have some diagonal entries that are 0, right? Namely this one. And that's okay as long as the diagonal matrix is all about what the off-diagonal entries are, right? So the off-diagonal entries are all 0 here. So that makes it a diagonal matrix. Okay, and then just one more example. Here's the case of a 2 by 2, right? This is a diagonal 2 by 2 matrix. All right, very good. The next type, special type, is what's called the identity matrix. And this is just going to be a diagonal matrix with all main diagonal entries equal to 1. Okay. All main diagonal entries equal to 1. Okay, and so a few examples. 1, 0, 0, 1. That's the 2 by 2 identity matrix. 1, 0, 0, 0, 1, 0, 0, 0, 1 is the 3 by 3 example. And the 4 by 4 follows the same pattern. Okay, and so basically just a diagonal matrix, but here we specify that the main diagonal entries all are equal to 1. Okay, and we'll see later why this is referred to as the identity matrix, what it does to other matrices when it's, well, what we'll see a little bit later, I think next lecture actually. Okay, and then a couple others. There's something called an upper triangular matrix. So an upper triangular matrix. This is a square matrix with all entries below the main diagonal equal to 0. So it's like a diagonal matrix, except you remove the restriction on the upper above the main diagonal. So it's a square matrix with all entries below the main diagonal equal to 0. Okay, so an example would be like this. 1, 2, 0, 3. Right, so everything below the main diagonal is equal to 0, and everything else is whatever. Right, so here's the upper triangle part of it. What about something like this? Is this upper triangular? Yes, indeed, right? Because if we, right, everything outside of this box is equal to 0, namely everything below the main diagonal. All right, very good. Right, and we can similarly define a lower triangular matrix, right? So I won't write it out, I'll just state it. Right, but obviously a lower triangular matrix would be just a matrix where everything above the main diagonal is 0. Okay. All right. Okay, so that's just, so what have we done so far? We've defined what a matrix is. We've talked through some of the conventions of matrices, some of the notation that's used to describe the matrices. And we talked about a handful of interesting or important types of matrices. So namely square matrix, diagonal matrix, triangular matrix. I think that's it. Identity matrix. Yeah. So we'll obviously come back to discuss those a lot more later, but that's a good starting point. Just get some of these ideas out there. Okay, now let's talk about operations with matrices. So how do we, for example, add matrices? Right, if I have two matrices and I want to add them together, how do I do that? Well, let's define that. Let A and B both be m by n matrices. Okay, then we say the sum of A and B is the m by n matrix, and then we say A plus B, whose ij entry is equal to aij plus bij. Okay, that's the sort of definition of the sum of a matrix. Okay, so for example, if I have A11, A12, A21, A22, and I want to add to that B11, B12, B21, B22, well, I'm going to get a matrix, right? So the way I would do this, I would add corresponding entries. So A11 plus B11, and then A12 plus B12, A21 plus B21, A22 plus B22. So it looks like that. Okay, so that's what Aij plus Bij means. That's a B. Okay, let's see an example with real numbers. A equals 1, 2, 3, 4, 5, 6. B equals 7, 8, 9, 10, 11, 12. So then A plus B, right, that's going to be equal to the matrix 1 plus 7, 2 plus 8, 3 plus 9, and then 4 plus 10, 5 plus 11, 6 plus 12. Right, and so when we add those together, what do we get? We get 8, 10, 12, 14, 16, 18. Right, and so this is our A plus B matrix. Alrighty, let's do another example. Find the sum of A equals 1, 2, 3, 4, and B equals 1, 2, 3, 4, 5, 6. So A plus B equals what in this case? Well, so in this case, if I try to add, there is a 1, 1 entry and a 1, 1 entry. There's a 1, 2 entry and a 1, 2 entry. But notice there's no 1, 3 entry in A. Right? So addition on matrices of different sizes is not defined. So in this case, because this is a 2 by 2 matrix and this is a 2 by 3 matrix, the addition of these two matrices is undefined. So A plus B is undefined. Right? We don't define addition of matrices on matrices where the sizes are distinct. Okay, so to add two matrices, they must have the same dimension. All right, no problem. So that's what we mean when we talk about matrix addition. Let's talk next about scalar multiplication of matrices. So like with vectors, there's different types of multiplication. So in the case of vectors, we talked about the dot product. That's a type of product that can be that's defined for vectors. We've also talked about scalar multiplication for vectors. And so for matrices, the scalar multiplication is it perfectly mirrors vector scalar multiplication. So let A be an m by n matrix, right? And let C be a real number. just put it like this. Then the matrix, and we'll denote it by C times A, is the matrix whose ij entry is C times Aij. Okay, and so basically scalar multiplication for matrices works exactly like scalar multiplication for vectors. So C times some matrix A11, A12, A21, A22. When we do this scalar multiplication, we're going to multiply C by every entry in the matrix. So you would get C times A11, C times A12, C A21, and C A22, like so. So this would be C times A. Okay, an example with some actual numbers would be like 10 times A. And maybe A is equal to 2, 3, 4, 5. Right, so that's 10 times 2, 10 times 3, 10 times 4, 10 times 5. So obviously that's 20, 30, 40, and 50. Okay. And of course this is where A is equal to 2, 3, 4, 5. I probably didn't need to say all that, but that's okay. And so as you can see, this definition really does, it perfectly mirrors vector scalar multiplication. All right, now something to note here. Note that the scalar 0 times A is equal to the 0 matrix. Right, so if A is an n by n matrix, then 0 times A is equal to the 0 matrix. And this is for any matrix in, the space of n by n matrices. Right, and this is notation that we may use to denote the 0 matrix. Because if you write 0 times A equals 0, that gives the impression that this scalar times this matrix is equal to the number 0, which is not true. I mean, you still have a matrix form here, just all the entries would be 0. And so the way to distinguish these two is through this subscript on the 0 with an m and n. Right, so this denotes the matrix whose entries are all 0. So 0 mn would be equal to 0, 0, dot, 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 0, 0, 0, dot, 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 0, 0, 0, dot, 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 0. Right, where there are, in particular, m rows and calls of zeros. Okay. All right, and so that's a fact. So any matrix times the scalar 0 turns the matrix into the 0 matrix. Okay, now notice that that this is true too. So if we have a matrix, what do we mean by the matrix negative A? Well, just like when we have like negative x in algebra, we know that that means negative 1 times x, and that's the case here. So this really means negative 1, the scalar, times the matrix A. Okay, and so so if A is equal to Aij, then negative A would be equal to negative Aij, right? So all of the entries would be negative, that you'd basically flip the sign. Okay, and from this we could define subtraction of matrices. Right, we can define subtraction of matrices to be if you have A minus B, then what that means is A plus -1 times B. Right, so another way to say that would be A plus -B. Right, and so in the case of subtraction, it's really just like AII minus BII. AIJ minus BIJ, right? So you just subtract the entries. So this would be AIJ minus BIJ. Okay, that's what the entries are going to look like. All right. Very good. Let's go ahead and, now that we have kind of matrices and we have operations with matrices, let's talk about all of the properties of matrices. So here comes the obligatory laundry list of properties. Okay, so let A, B, and C be in the matrix set MN, MMN, and let C be a real number. Okay, then, right, here we go. So what can you do with matrices and these operations? So first of all, you have A plus B is equal to B plus A, right? So this is commutative addition. Okay, so commutative addition. I won't write out all the names. I think people are probably familiar with that. So A plus B equals B plus A means that matrix addition commutes. It doesn't matter the order. And we also have associative addition. So A plus B plus C is the same as A plus B plus C. Right, so this is the associativity of addition, matrix addition. And we do have an identity element of addition as well. Right, and so in particular, if I take the 0 matrix in MN and I add that to any A, then that commutes naturally and is equal to A. Right, so there is a matrix that I can add to any A to not change A that will result in no change to the entries of A, and that's the 0 matrix. And we call this the identity element. Of addition. Additive identity addition element. Identity element of addition. Okay, and then we also have inverses under addition. So if I have a matrix A and I add to it -A, then I get, well, then that can be flipped too, so everything commutes, we know that, but that can be equal to, or that will be equal to, the 0 matrix. We call this the inverse element of addition. Right, so this is true for any A, right? That makes sense. And then we have two properties of scalar multiplication, and specifically the distributive property of scalar multiplication. So the first one looks like this. If I have a scalar times a matrix sum, then I can break the sum apart and separately apply the scalar multiplication. So that's CA plus CB. Right, this mirrors the distributive property that we're all used to. And it's also true if I have two scalars times a matrix, then I can take C times A and add to that D times A. Right, so these are distributive. Scalars. Distributive scalar multiplication. Okay, so it works like you'd expect it to work. No tricks yet. Okay, and then associativity of scalars, right? So if I have C times D, two scalars multiplied together times a matrix A, then it's perfectly fine for me to break this product of scalars up and do the addition or do the multiplication separately. Right? I could do C times the matrix DA, and that'll produce the same matrix as C times D times A. This is just associativity of scalars. And the last item on here is the identity element of scalar multiplication. So there's the number 1, right? A real number. And 1 is such that when I multiply it times any matrix A, I am left with A. Okay, so that works for matrices. Now, a lot of these things are common sense, but you know, it's important to know, and as you kind of go forward in, you know, algebra in particular, you're going to encounter algebraic structures that don't always follow these rules. And even with matrices, when we get into the next section, we start talking about matrix multiplication, we'll discover that matrix multiplication has some properties that where there are some places where it deviates from what we might expect. Okay, and we'll get to that when we get to that. But it's important to know these properties, to think about these properties, especially as we start to write proofs and we start to try to prove properties of matrices. It's important to know, for example, that the order doesn't matter, or that I can add in a different order and get the same result, right, etc. So let's prove a couple of these. They're all pretty easy to prove. Let's prove the first one. Okay, let's prove that A plus B equals B plus A. Okay, so let's do this. So we'll let A equal Aij, and we'll let B equal Bij. Okay. Then what can we do here? Well, we can say A plus B is equal to Aij plus Bij, right? And by definition, we know that that just means Aij plus Bij, right? Simple. That's just the definition of matrix addition. And it turns out that, you know, once you're inside the matrix, the components, the order of the addition definitely doesn't matter, right? This is just a real number plus another real number, so it is perfectly legitimate for me to flip the order and write it like this, right? And then I can just reverse the process, and I have Bij plus Aij, which is B plus A, right? So that's just a simple way to show that matrix addition commutes. All right, and something similar can be done for associativity of matrix addition. All right, so here's a proof of item 2 that, let's see, A plus B plus C equals A plus B plus C. It's going to work the same way, right? So A plus B plus C, right? That's equal to, well, you've got the Aij matrix plus, and then you've got Bij plus Cij. All right, so this indicates that I should add these two first. And so I have Aij plus, and then inside I've got Bij plus Cij. Okay, and then I add all three together, and I have Aij plus Bij plus Cij. Right, and then once I'm inside the matrix, we're talking about the entries of the matrix now, and these are just three real numbers added together, and I know that, you know, just from properties of arithmetic of real numbers, I can add them in any order I like, and so I can reassociate them like this. Okay, and then I can reverse the process. So now I pulled those two matrices apart, but I'm indicating that they should be added together first still. And so this is A plus B plus C. Okay. So this is an example of just taking the matrix itself, moving into the entries. Once you're inside the matrix and you're reasoning about entries themselves, then you're just talking about real numbers. You can do whatever you need to do with real numbers, and then you just reverse the process and you see that it works out. Okay. And then let's try one more. Let's try a proof of item 5. So 5 says that I can do this. C times A plus B equals C times A plus C times B. Let's look at that one. Okay. So we'll start with this side over here, actually. So we'll say C times A plus C times B. Well, we know that that is just C times Aij plus C times Bij, right? And so scalar multiplication means this is just C Aij plus C Bij. Okay, so just doing the scalar multiplication part of it. And then matrix addition means I add the corresponding entries. So this would be C Aij plus B Aij, or sorry, shoot, C Bij. I messed that up. Sorry about that. Let me just rewrite it. It just, so C Aij plus C Bij, like so. There we go. All right, so now we're describing the entry itself, right? So we're talking about real numbers now. Okay, and so I could always factor a real number. You know, these are two numbers, they have the same common factor, so I can factor it out, right? So I can do this. I can go C times Aij plus Bij, like so. And then this is a constant. This is the Ij entry of a matrix, and so that means this is just C times A plus B. Right, so you can see we went from this to this, which is what we needed to do. Okay. And so I think that's a good place to stop. The others are similar, you know, so like they all kind of follow the same sort of pattern. Start with the matrix notation, move into the entries, do what you need to do inside the matrix entries themselves, and then reverse the process. Okay. Let's define the transpose. So if A is an M by N matrix, then the transpose of A, and it's denoted A with a T superscript. So the transpose of A is the N by M matrix whose Ij entry is the same as the Ji entry of A. Okay, so to transpose a matrix means you're going to be changing the rows of A into the columns of A transpose. Okay, so let's see an example here. Let's see an example. So kind of take a simple one, A11, A12, A21, A22, A31, A32, right? So here's A. Then A transpose, right? So what we're going to do when we transpose this is that these three values will become the first row of the transpose matrix. So A11, A21, A31. right? And then A1, 2, A2, 2, A3, 2. Right, so this guy here becomes this guy here. Right, so literally your rows become your columns. So the first, everything with a 1 column becomes the first row. Everything with a 2 column becomes the second row. Okay, let's do an example with real numbers here. So A equals 1, 2, 3, 4, 5, 6. Then the transpose of A, well, 1, 3, and 5 are going to become the first row because they're the first column. Here they're going to become the first row of the transpose. 1, 3, 5. 2, 4, 6, because it's the second column of A, is going to become the second row of A transpose. Right, so notice this is a 3 by 2, and its transpose is going to be a 2 by 3. Right, so these guys will change places in the transpose. So the transpose changes the rows of A into the columns of its transpose. All right, so 1 and 2 become 1 and 2. 3, 4 become 3, 4. 5, 6 become 5, 6. Okay. Let's do another example of this here. Let's say we have A, and A is an upper triangular. So 1, 2, 3, 0, 1, 2, 0, 0, 1. If that's A, and A, so A here is in the upper 3 by 3 collection. Right, so this is the set of all 3 by 3 matrices that are upper triangular. Then what happens with the transpose? Well, 1, 0, 0 becomes the first row. 2, 1, 0, that column becomes the second row. And 3, 2, 1 becomes the third row. Okay, so A was upper triangular. Now A transpose would be lower triangular. So A transpose switches to the lower 3, 3 collection of matrices. Okay, so just an interesting feature. All right. And so transposes will play a central role in what's to come. We'll talk about them all the time. And let's knock out kind of a big theorem for transposes. So let A and B be m by n matrices, and let C be a real number. Okay. Then 1, A transpose. So if I have the transpose of A and I transpose it again, what do I get? I get A. Very good. Okay, so if I start with A and I transpose it, then I got A transpose, don't I? And if I transpose A transpose, well, I get back to A. That's kind of obvious on the surface, hopefully. So you can play with that one. I think it's pretty easy to prove, actually. But what about this one? If I have a sum A plus B, I add two matrices together to get a third matrix A plus B, and I transpose that third matrix. That's going to be the same thing as transposing A, transposing B, and adding them together. All right, so we can prove that one as well. And then this one is pretty obvious, but if I have a matrix C times A and I transpose it, then the scalar multiplication doesn't really make any difference. It's not too important there, right? So basically the scalar can come out and it can look like this if you like. Okay, so I mean that seems obvious because a scalar the scalar multiplication, it doesn't care about the size of the matrix, right? It's all just about the, multiplying each entry uniformly against C. So the fact that it's transposed doesn't make any difference. Okay, let's prove this one. We'll prove number 2 here. Let's walk through a proof of this one. Okay, we're gonna show specifically that A plus B transposed is equal to A transpose plus B transpose. Okay, so first thing we need to know is that, so there's 2 things here. First, we need to know that A plus B, so first we will show that A plus B transpose and A transpose plus B transpose have the same dimension. They need to have the same dimension if they're equal, right? So that's the first thing to show. And then secondarily, we'll talk about the IJ entry. Right, so let's see. A plus B. So A and B are assumed to be m by n. So the product, the sum of A plus B is m by n as well. Okay, that's just the definition of adding matrices. It doesn't change the dimension to add matrices. Okay, and A plus B so this implies that A plus B transpose is n by m. Right, and that's because the rows become the columns become the rows, right? So if this guy's m by n, then when we transpose it should be n by m. Okay. Okay. Now let's talk about this guy. What is this? So A is m by n. That implies A transpose is n by m. Okay. B likewise is m by n. That implies that B transpose is n by m. Right? Similar, same thing. Right? So if I've got A transpose and B transpose, they're both n by m, then A transpose plus B transpose is n by m as well, right? And so there we go. So those two are equal in dimension. Their dimensions are equal. Okay, that's the first part of the problem. And so what we need to show next is that next we will show that the IJ entries are the same. Okay, right, so namely the IJ entry of A plus B transpose and A transpose plus B transpose, right? So over here you're going to have AIJ plus BIJ transpose, and we need to show that that's the same as this one. Okay, and so let's start by defining, let's let A equal AIJ, and we'll let B equal BIJ, right? So we need to be able to reason about the IJ entry here. Okay, so that means A plus B is equal to AIJ plus BIJ. That's what happens to the IJ entry, right? Okay, what happens when I transpose that? So when I transpose it, you're going to get AIJ plus BIJ transpose. And that's basically what that's going to do. Is going to flip the subscripts, isn't it? So it's going to be AJI plus BJI instead. And we can reverse that. Sorry, we can pull those two apart, right? So now you've got AJI plus BJI. Okay, and now notice this is just the IJ entry of A transpose, right? And so this is just equal to A transpose plus B transpose. Okay, so we've shown that the ij entry is the same. Right? One, you start with the ij entry of this, and you find that it gets you to the ji entry of that. Right? And so they must be the same. Okay. All right. So this, together with the fact that the dimensions are the same, means that the two are equal. Okay. All right. Very good. Very good. Let's talk about what do we mean when we talk about a symmetric matrix? Let's see here. Okay. A matrix A is symmetric, and that's what we're defining, if and only if A is equal to A transpose. Okay. And so this is what we mean by symmetric. So A needs to be equal to its own transpose. We'll see an example of that in a second. There's a second concept here called skew symmetry, and we say that a matrix A is skew symmetric if and only if A is equal to negative A transpose. Okay, so there's two kinds of ideas here. There's symmetric, and then there's this idea of skew symmetric. It turns out they're actually very similar concepts, but let's explore what this means a little bit. Let's do an example of a symmetric matrix, and we'll see here. So in some sense, this is really kind of a straightforward idea, but in another sense, it maybe isn't. So -1, 0, 4, 0, -3. So here, we'll say this is A. Okay, now one thing you'll notice is that if you've got the diagonal here, if you look across the diagonal, there's a symmetry, right? So 6 is equal to 6, 4 is equal to 4, 0 is equal to 0, right? And so what that means is that when you transpose it, you end up getting the same matrix. So if I go 2, 6, 4, that becomes my new first row. 6, -1, 0 becomes my new second row. 4, 0, -3 becomes my new third row. Right now what you'll find is that the entries exactly correspond, right, because of the symmetry. So A equals AT implies A is symmetric. Now that's the idea of a symmetric matrix, and by definition we say it's symmetric if it's equal to its own transpose. Here's another example. 0, -1, -2, 1, 0, -3, 2, 3, 0. That's A. Then when we transpose that, what do we get? Well, we get 0, 1, 2, -1, 0, 3, -2, -3, 0. Right, now notice here, we'll go back to A. The cross entries are not exactly the same, right? So this is a 1, this is a -1, this is a 2, this is a -2, 3, -3. So skew symmetric means that the symmetric elements are plus or minus each other, or they're negatives of each other. They're inverses of each other. Right, so that means, so then when you transpose A, you see all the negative entries drop down into the lower sections. Then they start at the top and they end up in the lower section. Right, so in this case, A is equal to negative A transpose, because negative A transpose is -1 times this, which gets you what? 0, -1, -2, 1, 0, -3, 2, 3, and 0. right? Now, and this guy here is the same as that, right? So A is equal to negative A. Okay, so in this case, A is skew symmetric. Right, now, something to notice here is that the main diagonal elements of a skew symmetric matrix must be equal to 0. Okay, they must be equal to 0, right? And that's because they're the only elements that don't change places during the transpose. Okay, so if you notice up here, for example, 2, -1, 3, 2, -1, -3. They don't change place. And I guess it's clearer in this example. The 0, 0, 0, they all stay in the same place. Right? But A is equal to negative A transpose. So let's just say that one of these entries was 8 instead. Right? Then it becomes this. Right? Then if I multiply A transpose by -1, the 8 becomes -8. Right? And then in that case, they don't align. Right? So AII needs to equal negative AII. So the diagonals of a skew symmetric matrix must be 0 because AII equals negative AII only when AII equals 0, right? And so since the diagonal elements don't change places, they have to be 0. Okay, very good. Very good. All right, and now we'll have our first kind of nice big theorem here, and then we'll call it quits for this section. So this is a theorem, the first of many decomposition theorems from linear algebra. So every square matrix A can be decomposed. Okay, it can be decomposed uniquely as the sum of two matrices S and V, where S is symmetric and V is skew symmetric. Okay. And in the case of this theorem here, S is going to be equal to 1/2 A plus A transpose, and V is equal to 1/2 A minus A transpose. Okay. And so what does it mean for us to say that A can be decomposed? Well, what it means is that A is equal to S plus V. So A is decomposed. That's what we mean by decomposed in this sense, right? We can pull it apart. We can kind of rewrite it in a particular form. Okay. Let's prove this theorem. This is an interesting one, and then we'll do an example. Okay, this is an interesting theorem. It's a nice, relatively simple proof, but a little bit more involved than what we've seen. So first, let's show that S is symmetric. After that, we'll show that V is skew symmetric. And then finally, we'll show that A is equal to S plus V. So first item, S is symmetric. Okay, so what do we need to show? So we wish to show that S equals S transpose. How can we do that? Well, all we need to do is we start with S transpose, and that is equal to 1/2 A plus A transpose. Okay, and now what we're going to do is we're just going to use the properties of the transpose that we discussed previously in the prior theorem. So that means we've got 1/2 A plus A transpose transpose, like so. And that means we've got 1/2. Now remember, if you have a sum of two matrices and you're transposing the sum, you can bring the transpose in. So it'll be A transpose plus A transpose transpose, like so. And so that means you've got 1/2 A transpose. And what's the transpose of a transpose? Just the original. Right? And we know that matrix addition commutes. And so this is 1/2 A plus AT, and so that is just S. So ST equals S. Okay, these are just properties of the transpose. Okay, so item 2 then, V is skew symmetric. Right, when we wish to show that V equals negative V transpose. Okay, and so we'll start with negative V transpose. All right, we know what the form of that is. It's going to be negative 1/2 A minus A transpose transposed. Okay, and so we know that's negative 1/2, and then it's A minus A transpose transpose. And similar to what we did before, we'll move the transpose inside. So negative 1/2, and then it's A transpose minus A transpose transpose. Okay, and we know what happens. That's negative 1/2 A transpose, and the transpose of transpose is just the original. Okay, so we get to this pretty quickly. And you can think of this as negative 1 times 1/2. Right, so let's just multiply everything by negative 1 here. And so we get 1/2, and then it's A minus A transpose. I kind of did 2 steps there, so I multiplied it all through, and I changed the order because of the commutativity. But you can see that that's perfectly reasonable. And so this is equal to, well, this is just V, isn't it? Okay, so you've got negative VT is equal to V. So the negative transpose is equal to the original. Okay, so that means V is skew symmetric. And then finally, we need to show that, switch pages here, we need to show that A is equal to S plus V. Well, this one is very easy to show, right? You just start with S plus V, and then you just add them together. So 1/2 A plus A transpose plus 1/2 A minus A transpose. Okay, and so go ahead and use the properties of scalar multiplication to distribute the 1/2. And so you get 1/2 A plus 1/2 A transpose plus 1/2 A minus 1/2 A transpose. Right, and then you can regroup these things. These are just matrices, so they all can be added together in whatever order. And so I have 1/2 A plus 1/2 A, that's these two, and then these two, plus 1/2 A transpose minus 1/2 A transpose. Of course, that's equal to the 0 matrix. And so I have 1/2 A plus 1/2 A, right? I can rewrite that as A, right? Basically A. So each of the entries is a half, and now I add 2 of them together, I get the whole entry. And so this is just going to be A, and then plus the 0 matrix, so it's just A. Right, so A is equal to S plus V. And so that gets us all we need. So we know that the S is symmetric, V is skew symmetric, and we know that S plus V is equal to A. Okay, perfect. Let's do a quick example using this. Let's decompose the matrix. All right, here's our matrix: -4, 2, 5, 6, 3, 7, -1, 0, 2. Okay, so we'll start by calculating S. So S is 1/2 A plus A transpose. Okay, so it's just 1/2. And then you've got A, -4, 2, 5, 6, 3, 7, -1, 0, 2, plus A transpose. So now I have to transpose the rows. -4, 6, -1, 2, 3, 0. Oops, sorry. So sorry. -4, 6, 1, -4, 6, 1, -4, 6, 1, 2, 3, 0, 2, 3, 0, and then 5, 7, 2. Okay, and so I get 1/2, and then I get -8, 8, 4, 8, 6, 7, and then 4, 7, 4. And I can divide all of the entries by 2 or multiply by 1/2, and I get -4, 4, 2, 4, 3, 7/2, 2, 7/2, and 2. Okay, now notice that's a symmetric matrix, right? 4 and 4, 2 and 2, 7/2, 7/2. We can do the same thing for V. V is 1/2 A minus A transpose. And I'm just going to kind of skip to the punchline here. And what you'll get when you do this is 0, -2, 3, 2, 0, 7/2, -3, -7/2, and 0. Okay, so you get this guy. Notice this is skew symmetric. 2, -2, -3, 3, -7/2, 7/2. Right, and you can easily verify by adding these together that S plus V does in fact equal A. Just basically add this matrix and this matrix, right, and you will get the original. Okay, all right, very good. We will end this section here. In the next section, we'll get into matrix multiplication, which is a totally different thing than any kind of multiplication you've ever seen before, unless you've seen matrix multiplication before. So we'll get into that next time, and then we'll be off to the races and ready to move into some of the more complicated and interesting stuff. So, all right, take care until next time.